Okay, hello everyone. I'm Ido Barkan. I'm an architect at AppsFlyer, and today I'm going to tell you a story about a large-scale NoSQL database migration we've done of one of our largest databases in AppsFlyer about a year ago. I'll start by talking a little bit about AppsFlyer. I'll present you the context so you'll know what we do and how we use databases. And then I'll talk about a little bit about the condition we had, the motivation we had to move technologies, and what were the limitations. Then I'll explain what we've done and why, what worked for us, what didn't work for us, and then a short summary with some lesson learned. Okay, so AppsFlyer is basically a software as a service that is designed to support marketeers in optimizing their mobile app campaigns. By doing so, it processes many events that mostly originate from seller phones around the world, and the throughput is rather high. We serve and process around 25 billion events per day. This is the last up-to-date numbers. And the heart of the software as a service is actually a data pipeline that serves the events, processes them, and it has an internal state. The state is mostly supported by a few very large NoSQL databases. So the database in question here is our install database. You see it's a Couchbase already. The general architecture is microservices, and this is a common pattern in AppsFlyer. There is one service that writes to the database, and another one, sometimes quite a few, read from the database. So this is the numbers. We write about 2K write IOPS and read about 180K read IOPS. So we can guess that the database is rather large to support the data and the IOPS, and also that it is read intensive. Of course, it's a mission critical database because it holds our installs, the app installs, very important customer data. Okay, but we need to replace it. Why do we need to replace it? Basically, Couchbase was fine. It brought us until that point, but it went bigger and bigger, basically scale out of control. 45 instances, rather large instances and expensive on its last days. XDCR couldn't keep up with the write rate, which was rather low. Daily backups lasted more than a day and didn't back up the whole database. We weren't happy with the support, and we've started looking for another solutions. We did a few POCs, some investigation, some research. We decided to go with ErrorSpike. And okay, so we need to replace it. So how big it is? Very big. As I said, 45 machines, around 2 billion records replicated by a factor of 3. Very read intensive, as you see, 180K IOPS, and costly, $30,000 per month just for the hardware without any license. And we had a few months to replace it until our enterprise plan is due. We need to get rid of this database and move it to a new one. Of course, needless to say, mission critical, has customers' data. We cannot afford any data loss or downtime. Okay, so data migration is already a hard thing to do always, even when you're dealing with conventional relational database. But in NoSQL database, it's even harder and messier. Why? Because basically there is no common denominator between any technology. To start with, there are hundreds of technologies, hundreds of NoSQL database out there in production. Every technology uses a different schema or a different data representation. Sometimes there is no schema at all. Even if there is one, it is represented differently on several databases. even the standard query language doesn't exist. Some support SQL, some support Nickel, some support HTTP. It's a jungle. And when it comes to migration tools out of the box, you're all alone. Just do it yourself. So we did it ourselves. Mission is to migrate this entire monster with no downtime and no data loss under production. Okay. Now I'll start explaining the concept of what we've done and what worked for us. The basic idea here is to use the application itself, the application code, to migrate your data between the old database and the new database. So first step is very easy. First step, just duplicate your writes and your updates to the new database. It's important to say that reads are still served from the old database. We hate it, we want to get rid of it, but it worked for us, it is working, it is functioning. We're not sure what is about to go on our new cluster. We just duplicate data. So we can start small here. We can start with a very small and cheap database and grow up as we go. Okay, it's important also to say that the entire data in the new database is completely redundant. If you find out a bug, if something doesn't look right, it's okay. You can wipe out the entire database, start all over again. And this is also a good time to get to know your database. See how scaling out works. Do some data sanity. See if a record here looks exactly as a record there. If it's TTL, if you use any TTLs, is identical. Look at its logs, try to backup, try to restore from backup, try to cause node failures. This is the time for playing games and to get to know your database. Okay, now take a break. Take a break, breathe. It's time for testing, right? So data is accumulating up. Is the sizing, is what you thought it would be? Is the load, is what you expected? I know the load is without any reads, but still, if you're write intensive, it's something to look about. It's important to, now it's a good time to configure metrics, to configure alerting based on the metrics, look at the logs, get to know them. I've talked about backups already. And let the database live a little, get to know it. Okay, for the second phase. Second phase is a little bit more complex, but it's very simple. The idea here is start serving from the new cluster. So what we've done is that we started serving from the new cluster, and the application code was written such that for every record that needs to be served, it was searched on the new cluster, and we didn't find it, we fell back to the old one. What does it mean? It means that the record wasn't migrated yet. Maybe it will be migrated in the future. But if it is on the old database, we can find it there. The most important thing is to configure a metric corresponding to this fallback. I call it the miss hit metric. So whenever a record is found, wasn't found on the new database and was found on the old one, you count one more and you have a dashboard on it. Why this metric is so important? Because when this metric diminishes to 0, you know for sure that the migration is over. So have this metric configured and running. Also important to say, all the data is still being written and updated in the old cluster. So if you found any bugs, and you will find bugs because this is an application code here, you'll write bugs, just revert everything and go back to the original database. Wipe out your database, start from square zero. It's okay. Another thing is to go slow here. If you can go gradually, for example, serve reads only for synthetic data generated by your test, or data that is non-VIP clients, or a very non-important API. I don't know. If you can do it gradually, do it. You want your bugs to affect the not very important data. Second, breathing time. Let your database work. Okay? Now you're rewriting to it several days. It should get bigger. You're also reading from it. So I guess you will probably want to scale out even more to support the additional load. And basically every bullet that I talked about testing in the last breathing slide is relevant here. Retest everything. See that sizing is still making sense. The load still makes sense now. It includes reads and metrics again. And the most important metric is the miss hit metric. And don't rush. Let your database work. Traffic may vary, different times of day. Let it work for a week if you can afford it. Let it work in the weekend. Now your alerts are in place and your metrics are in place. So is that it? Sometimes this is it, because it depends on your access pattern. If you are very write intensive, and if the records are very short-lived, they have low TTL, those two phases are enough. The hit-miss metric will soon diminish to 0, and you'll know that you can get rid of your old database and just serve from your new one. But sometimes this is not true, and this is also not true for our data, because some records may live for a very long time, or maybe never migrated because they were never read by the application. And so we, and maybe you, will have a very long tail of data to migrate because you have to. It's data of the customers, and you just cannot get rid of it. So on to the manual phase. The idea here is to just stream the entire data set from the old cluster to the new cluster. What we've done is that we actually wrote two very little and simple services, a dumper and a loader. The dumper just reads the entire set of keys from the old database. I'll soon explain how this can be done. Streams every key and its metadata through buffer, a write buffer. We use Kafka here, but you can use every message queue you want to use. And then a loader just reads the key and insert it to the new database. Of course, do not overwrite anything because most of the records were probably migrated. Okay, so a question that you might ask here is, how in the hell do I list the entire list of keys from the database? Okay, so a small detail about views in NoSQL databases. So every database or NoSQL database have a views or something parallel to views. Some call it secondary indexes. Some call it, some doesn't call it in any name. For example, Redis has no naming for it. But similar technology exists in almost every database. An index, a view, a secondary index. I'll show what Couchbase has to offer, but other databases use very similar technologies. So Couchbase has a way to write JavaScript code, which is actually a function. They call it the map function. And the code, you can run it, the database management will run it on the entire set of keys, and possibly each key will be emitted by the emit function. The API is to emit a key and a value, and this creates an index or a view. We've decided to use for the key the expiration or the TTL of the record, and for the value the document ID, which is the key you query the Couchbase to get the record. Okay, so it's important here to say that views are not for free, okay? They occupy RAM, and they have, and they require quite a few resources to be created. Also, databases update the view while you keep write records to them. So it might be resource intensive. It also implicates that the document or the record itself should never be a part of the index itself, because you can see this is possible just to pass the doc here as the value. This will surely blow up your database, because the database will just have to replicate the entire set of keys and records into its RAM, and will surely bring the database to its knees. So we've created a very simple view here, the key, which is TTL, and the value, which is the ID itself. Also a nice feature of Couchbase is that the key is also the sorting key. So what we got here is basically a list of all keys with their ID sorted by their TTL, and for us it was very convenient because the keys that were about to expire, the oldest keys, we saw them first in the list, and those are actually the keys that we needed to migrate first, because they were probably not migrated naturally by the application. So this was nice for us. Okay, back to the manual mode. So the dumper just creates a view. It gets a list of the entire 2 billion keys from the database and their TTL, stream them through Kafka, which is the write buffer, and the loader just takes key by key and tries to update it insert it to error spike. Of course, do not overwrite anything. And all you have to do is just sit back, watch the miss hit metric diminish slowly to 0. And when it's done, it's done. You can stop this process in the middle. Also, you might ask, why didn't you guys started to do it to start with? Why this is only the last step? Because this can be done parallelly to the application migration code. No one needs to wait for it. The answer is that I just hinted that views are not for free. They have serious resources implications, and we just had to wait for the old database to go low on its read load, and for most of the records to be moved to the new database. And then we could only afford to just even create an index. If I recall correctly, the trivial index took about 5 or 6 hours only to build on the old database. By the way, a variation of this would be to also pass the records on the write buffer. It might be a bit wasteful, but what you can get from it is you can get Kafka to back up your database. So if you're about to close it and you're afraid you in some point in time want to back up from it, restore from it, it's also possible. We didn't do it. Okay, so the metric is 0. Everybody's happy. We have a new shiny database, and number of records is still around 2 billion. 2 availability zones, 2 clusters synced with XDR. Same IOPS, and the IOPS just keep growing. You can see that we have only 10 machines compared to the 45 machines we had before. Cost is around 1/3 of what we've paid before. And there wasn't any downtime, no loss of data. Okay, short summary, some lesson learned. So first of all, planning. So as for every software or operations project, this require a very thorough planning. Plans might change, but they're still important. It takes time. So plan ahead, plan the points you want to stop and test. Plan your tests. Plan what you want to test, what the invariants you want to look at. Second, go easy, go slow, go gradually. I am speaking here about the phase where you start serving reads from your new database. If you can do it to any non-important data, maybe clients, APIs, we use apps, so it was easy for us to go gradually. Even synthetic data for your test, do it first. You want your bugs to affect that first and not your client's data. 3, breathe, stop and test. Test whatever you can and plan those tests before you start. Configure your metrics, bring your database to the DevOps team to get to know it, know your logs, know your alerts, know how to back up stuff, how to restore. The first phases are the perfect place to make mistakes. You don't want those mistakes to happen when this database is under full production load. Fourth, at any phase, at any step, do not delete anything. I know it's tempting. You say, okay, my new database is working. It's a little tiger. It's a shiny new database. It's better than the old one. I can start deleting stuff that I know that were migrated. I'm all good. No, you're not good. Don't delete anything. Wait. Save your save point as a place that you can revert everything and start from zero. It's not funny to discover near the end that the data was not migrated correctly, data was ruined, you cannot restore from backups, but you discover that you already deleted data and you never go back. And in all the process I just talked about, at no point you delete anything from your database. And lastly, slower means safer. That's obvious to anyone, but safer also is costly. Mainly because you're getting paid, it takes time, you run 2 clusters, possibly in full-blown clusters in production, data is duplicated, and this might cost a lot of money, but don't forget that the other possible outcome is to lose data or to have downtime, and this might be 10 times more costly than just burning a few dollars on a second cluster. Those are dollars well spent. Don't feel bad about it. Okay, that's it. Can I have a question? Sorry, the question was if the numbers of money that I showed here were only hardware or additional. So no, I only compared the hardware. Licensing is something you can. Okay, so the question was what databases did we test with Aerospike? So we tried Redis Labs. We also tried Scale DB, and Aerospike won the race. So yeah.
She used to migrate the long-tail data. What happens if it fails? Do you have some sorting at the map reduce function, which you could use to resume the operation from the place it started?
Okay, so by fail you mean crash. So that's why we have Kafka. You know Kafka? Kafka is a message queue.
If you take everything once again from the code base, you have to sort it, or you have to identify the place to resume the operation, right?
Yeah. Anyway, the writing, the migration itself is idempotent. Okay, you don't overwrite everything. And it's also important that even in this phase, you still write and update the old database. So the database in the old database, the data in the old database is still up to date, even at this point. Okay? So worst case, just dump everything and serve from the old database. Just serve from the old database. But if you're seeing that, for example, the loader crashes, you have Kafka, all the data is still in Kafka or streamed into Kafka, you can just start over. Kafka doesn't delete the messages until they are overdue. It's not like Rabbit or something.
I'm more concerned with getting everything into Kafka just once. Like,
you can get it into Kafka 10 times. It doesn't matter. It's idiopotent. The dumper can write it 10 times, and the writer will only write it once, and will only write it if it's missing. So there's no problem to do this process again and again and again and again.
so basically, you assume that if dumper fails, you just run it over again.
Yeah, you just restart. Dumper is also nice because you can parallelize it very easily. Just spawn 6 of them and read as fast as you can from the old database and write as fast as you can to the new database. Depends on you. Thank you.